today's point. Okay, so page fault. So simple definition of page fault is, okay, you are here in the diagram. So now you want one page, okay, on the RAM, that's a physical memory. So that page is not present. So what is the option you have is take a present page out, bring the required page in. That is called as the solution. But page fault means whatever the page we need that is right now not available on the physical memory. It may be available in the disk, hard disk, or it may be available in the cloud. Okay, but thing is it is not available in the RAM. Okay, I hope you know the words cache miss and cache hit. So what we used to call cache hit and cache miss. So we used to write a processor like this. Okay, so this is a cache. Actually, it is both are on. So it want to execute a plus b. Okay, so a value is 10, but b value is not present in the cache. So it will try to access first in the cache. So cache doesn't have the data, so it will go for RAM, next level memory. Okay, so that is called as cache miss. Here two things happened. Cache hit for A because A value 10 is stored in the cache and it is available, but required B value is not present in the cache. Hence it is with respect to B cache miss, with respect to A it's a cache hit. I hope you understood now. Same concept with respect to page. Data, we need a data or we need a page to perform some activity, but that page is not present. That is called as page miss. Exact word, page fault. Okay, how the operating system deals with such a situation of page fault. Okay, first I will explain the diagram. You can easily. And one more thing is, please practice this diagram many a times. This is a definite question in either internal or in the university examination. Especially this, how to handle page fault. If you remember these 6 steps, okay, so that's itself an explanation for the diagram. Okay, now you see. Yesterday I tried to give you some idea that okay, so here I will draw. Okay, so you wanted a page A, page B, sorry, process A and process B. Process A want page numbers 10, 11, 12. Process B want 17, 18, and 19. It requires 19. Okay, so process C wants, yesterday I have took the same example, 80, 81, and 82. Okay, yesterday in the cylinder we have shown. So what were the present things? So 10, 11, 12 are already in the RAM. So PA, process A requirement fulfilled. No need to swap out, no need to swap in anything. Directly you will get all the required expected. Hence it is called as valid. Okay, now next. Process B want 17, 18, 19. But what are the present contents? 17, 18, 20. Okay, present contents are 20. So process this 19 is present in the disk. Okay, 19 is present in the disk, 20 is present in the physical memory. Two things are available, one thing is not available. With respect to process B, 20th page is invalid. What is the option we have? Take out the page number 20, okay, and store, shift it to disk. Okay, then so what was its requirement? Page number 19, it is available here, swap in. So what happened? And redefine this I to the new one, because all the contents are available. Hence PB, process B, successful. So what about process C? We have the pages from page number 1 to 35. But process C requiring 80, 81, 82. Now this is the only option we have is abort, because it is not at all possible to give the page number or a frame number, whatever it has requested. I hope you know. Definitely valid. Right now invalid because of swap in and swap out and swap in, converting into valid. Definitely abort. These are the three possibilities. Okay. So now you see here. Okay. See now, it requests something for a page table. Okay. That pages are not at all available here. That is 80, 81, 82. See, 80, 80, load yum is called as a frame number 80, 81, 82. See now, it will check in the OS. OS will transfer whether there are 80, 81, 82 are there. If yes, one type. If no, it will give no such a frames with respect to 80, 81, 82, and it will give. Okay, so actually, now comes what this page table will have, very important, starting value, starting frame, that's a 1 here, and end frame, that's a 35. So what is expected 80? So definitely what is the idea page table will have? It doesn't have more than 36. I hope you understood, more than 36. So what happens? For the process will request for 80, 81, 82. What is the upper limit of page table right now? 35. So immediately it will give the answer that it is not possible to solve. That is what the decision of abort. Okay. I hope you understood with respect to abort. Page one, request one, and immediately abort. But what about explanation of PA? That means process A, which needs 10, 11, 12. See now, what is 10 valid, 11 valid, and 12 valid? Why I'm telling you is, say for example, I will split this frame into, sorry, page table into like this: 10 V, 11 V, 12 V. V indicates what? Valid, because 10, 11, 12 are already there in the page table. Correct? So all are valid. Give the data, so it will work. I hope you understood. It will work. See, one reverse happens in two cases. What are the two cases? 100% success, because all are right now available. 100% failure, that is called as abort. But the sixth stage will come into existence when it is a partial valid and partial invalid. Hope you understood. So 100% failure means abort. Stage one, immediately out. So once again, PA, all are valid. Take this, and now the case PB, PB here. So let's assume this case, right? Okay, expectation is correct. 17, 18, 19. What is the present state? I will show here. What is the present state here? 17 valid, 18 valid, 20 valid. But what is the expectation? 17, 18, 19. With respect to 19, it is a I. With respect to 19, it is a I. Now is a decision. 20, first thing, whether 19 is present or not here. If yes, bring it. Okay, so what is our request? V for 17, because it is available. V for 18, that is also correct. I for 19 is correct, but 20 here is present, that is invalid. Okay, so that is invalid. Right. Now, trap means inform. Inform this that whatever is required by a process is right now not available in the page table. That is called as process. Sorry, trap. To whom? Operating system. So what operating system will do? It will find out where real address of page number 19 is there. Okay, it will calculate. That is called as address binding, either in the load time, or in the compilation time, or in the execution time. OS will calculate that address is tried to search in the disk. Okay, try to search in the disk. So that means the 19th was not present. Definitely that was missed. Now we brought whatever was missed onto the frame table. That's a physical memory, onto the frame table. So what happened here? Let me show you the diagram. 17 is present, 18 is present, and 19 we took right now. Okay, 17, 18, 19 are right now present. So what I do is, I will, sorry, I can have one more concept. Let me elaborate. If this table limit is 3, what is option I have? Option is I have to delete this 20 and load this 19, and 19 will become valid. If page table size is 40, what I can do, I can keep 20 as it is. I can newly add this 19 and making it as B. Okay, this invalid. Now, these three pages are referred and given the successful data for operation. I hope you understood. So any doubts, please you can ask. Before I could go for the previous slide in which we explain it in terms of text. Okay, I repeat once again, three scenarios: 100% success, 100% failure, and partial case. Best, worst, average. Best case 10, 11, 12. So the table is like this, like this. Okay, see now. First, let us explain for best case. 10 valid, 11 valid, 12 valid. Expectation is right now present, so immediately it will get a data. Worst condition. Okay, so now what happens? 80, 90, 80, 81, 82. Here, 80, 81, 82. Page number has a limit of 1 to 35. So requirement itself is cancelled. So abort for process 3. Okay. Now, it is an extra work when we have partial execution, correct, and partial are wrong. Like 17 valid, 18 valid. I am assuming a page table size of 3 only. So right now it is 20. But what is its expectation? 19. So with respect to 20, it is not required. So what we have to do? We have to check, is it possible to get the frames? Because 19 is present between upper limit and lower limit of 1 to 35. Yes, we have to check and decide. Okay. So now what happens with respect to 19, it will inform there is a missing in the expected or required page and give its data or address by binding method. That address is searched. The corresponding frame table in the physical memory is updated because it was a missing. Now it has been loaded successfully. So redefine the page table. Okay. If page table size is 20, you have to delete it and give. If page table is sufficient, then no need to delete existing. Please add the extra and make also that as a valid. So restart the instruction. I hope it got a resource now fully in the page table. It will fetch the data required and it will go for execution. I hope you all understood this case, and this is a very, very important diagram. So please practice this diagram and 6 simple steps. Don't miss the order also. Okay. Remember the order. Remember the 3 cases, how to explain so easily, and you should be able to get full marks for this concept, simple concept. It's okay. So let's go for the theoretical 6 points explanation. So what happened here? First, operating system will looks for the table. So if the request is not at all present, so abort. If request is present, request is possible to provide, so let's go for the steps. Okay, let's go for the step. Valid and abort, possible with the swap method. Okay, abort means not at all possible. Okay, next, trap the OS. Trap the OS. That means inform the OS. I hope you can see. Inform the OS. Third, search for the page in the storage. You can see here. Find the frame. Okay. So you have found the frame. Next, what? Bring that frame onto the frame table. So what is the step here? I think here. Swap the page into the disk. Which page you have brought, for that page you make valid bit attachment. Okay. Whichever the page you have brought, make that, earlier it was invalid, for that you make it as valid and restart the instruction execution. I hope it is clear. So this is called as converting page fault into page success. Okay, so simple way, if you don't have a textbook with you for preparing the examination, you have two options. But final decision is what? Final decision, you should have textbook either by getting a from a college library or getting it from the market. But thing is, you should make it available. Okay, so then only you can study and appear for examination. What happens if you don't have textbook or if you don't have corresponding study material? So probably it is not easy to pass the examination. Okay, so in this way, okay, please practice this diagram. Okay, now, so what do you mean by demand paging? So supply the page only when there is a demand. If there is a request, then only we have to load. See now, as I told, 19th, 18, 19, sorry, 17, 18, 19 was a request. What we assumed is 17, 18, 20. 19 when it has brought from disk onto the table, only when process B has requested. If process B was not requirement of the page number 19, where 20 was present, 19 was requested, it is no need to change it because there was no request, no need to change. Okay, so that, as I mentioned, never bring a page until it is required. That is called as pure demand paging method. Only after the request we have to change. Okay, so now what happens whenever we have multiple access? Okay, so one process may request for that resource right now, some other process may request for the same resource little later. So this is called as some multiple access, multiple pages. Okay, sometimes same process may request for multiple pages also. As I took, as I said, example page, process A requesting 10, 11, 12, B requesting 17, 18, 19, like that. Okay, there is no rule that only one page is missing. There may be multiple page faults also. Okay, see, the situation is like this. Process A, B, C, they all the three will come. Process A has a highest priority. Page table capacity is also 3. See here, process A, B, C, 11, 10, 11, 12. See, this size is 3. That means, oh, sorry, if you assume it as a 4. So what is the case? Let me draw this idea. Process A, 10, 11, 12. Process B, 11, 12, 16, 18. Okay. Process C, 18, 19, 80, 80. Okay, see this case, if you assume it as a 4, size of 4. So what happens? 10, 11, 12, correct. This is not a problem. All are hit. 11, 12, okay, what we can do? 16 I can load because size is 4. 11, 12, 16. Okay, let me erase this for time being. So what happens? Page success. Now what happens? If expectation is more for 18, okay, suddenly process B has a highest priority than process C. Now what we have left with option? Process B priority is important than process A. So now what we can do to finish a process B, 11, 12, 16, 18 is required. 11, 12, 16 are already there. Process A has a less priority. So what I can do, I can remove this 10. I can place here 18 so that process B, whose priority is more, I can solve this. I hope it is clear. Once it finishes, what I can do is I can remove 18 and bring back this 10, and so that process A will finish later because it's less priority. What about process B? Process B, 18, 19, 80. So hope process B and A finishes. I can take 18 valid, 19 valid, but with respect to 80th page, always it is not possible to finish because one part of a resource is not possible to give because that is itself not at all present. See, this is called as multiple miss or multiple hit. Okay, not all the time single page may get miss. Okay, we have three methods for handling the page misses. Okay, so page table with a valid invalid bit, I think you know that. If it's a valid, pages are there, maybe you need swap in swap out. Invalid means definitely page is not at all present. Secondary memory, pages are there in the secondary memory, bring them. That's the solution. So instruction restart. Instruction restart, that means recheck whether you need same pages or any of the existing pages. Is it possible to finish a work by any of the existing resource or not? Okay, there are how to explain most worst condition of this paging. Most worst condition of this paging is first step, trap the operating system. That means inform that page is not available. Second thing, whatever we are doing the work, that values should be stored as a in the register. Third thing, mention this page not availability as interrupt. Now the condition why it should be mentioned as an interrupt. Say for example, what happens, you are taking some examination. Okay, you are taking a classes, you are attending a classes. Some of the notice will come from the office that you have not paid a fees, so bring the fees. Okay, so what student will do, he may neglect the message from the office, but whenever it is examination, uh, pay the fees, otherwise we will hold the hall ticket, then he will take a serious. That means whatever is missing, give some priority. If we give some priority, definitely the other person will go for with some importance, he will try to do that activity. Okay, so give some important, whether it is very much important, moderate, or not at all important. Like that, a process should decide whether that missing page is important or not. If it is important, yes, please bring the page as soon as possible. Like that, we can inform. Now, so check whether the page is really valid or not. As I mentioned, 20th 19th page you have required, no, you have requested, so that page is possible to serve. What about 80th page? That's a illegal. I think legal means page is there but right now not available, that we can get it by swap in swap out. If page 80th is requested, that becomes illegal because that frame itself is not available. Okay, once you raise the interrupt and check whether it's a legal or illegal, now the condition, sorry, now the work, now it is decided, yes, the 20th page, sorry, 19th frame is legal, and get it. See now what everything will do, processor will concentrate here and it will try to search that frame, it will bring and update the physical memory as well as page table. So during this, it is called as memory interaction. This is called as memory interaction. What processors should do during this fetch? During this fetch is, okay, give the same resource of CPU to some other process instead of wasting the time. That is what a concept in we are studying here. See now our process is doesn't have all the resources available, so our process should enter the wait queue. Until what it should enter? Until 19th frame searched, loaded back and updated. Until that our process enters wait state. Okay, so wait state. Next, during a wait state, computer will search the hard disk. Computer will search the hard disk and it will transfer. So again, during this transfer, give the CPU for some other user. Why? Because you are not working on a data, instead you are working on memory. Correct? So some other instruction we can execute. Okay, after receiving the interrupt from that disk. Okay, so say suppose disk is also busy with some other work. So our request of frame 19 is little late. Then what we have to do? We are in the wait state. We should continue in the wait state. Once that disk finishes its earlier work, then it will take our work as the queue. Then it will give us the frame. Okay, so receive that interrupt, then save the register. Now the data is back. Okay, so the data is back. It will also stores the data. So then determine whether the interrupt is from disk. See this case, whether this 19th frame we got it from the hard disk, or sometimes is a case even that data is also not available in my computer. It may be available in some cloud. So get it downloaded, then take into the execution. See the case how it will get expanded. Now once you got a data, page is uploaded on the memory because either from the hard disk or from the cloud you have downloaded and page is available. So then after page is available, now it is allowed for Okay, now page is available. Is CPU busy with the other process when we have given CPU to some other user when we were trying to fetch this? If that process is completed, okay. Otherwise, again we have to wait because CPU is busy in the some other. Very simple way. What I would like to tell you once in a real scenario is you wanted to collect a ticket. Okay, you wanted to collect a ticket, some counter. Okay, so what happens? You will give 500 rupees. So okay, so some amount you will give. He doesn't have a change. So what he will do? He will issue a ticket, but he will not give us a change. So he will keep us waiting. Okay, right? So he will keep us waiting. What he will do is he will collect the amount from next person or one or two, and he will issue the ticket for them. Then once the minimum cash is available with him, he will give the changes. Same way, we waited until what? The CPU is whatever for whom we have given the CPU, that should finish. Finally, once everything is available, that cache is given for us and will go out. Same way, once the CPU is free, it will finish its work and we will go with our new table of the page for further execution. This is a most worst case. You have to remember this is 6 steps and these 12 steps in the worst case. Okay, right now performance measuring. Okay, see, now there are three major activities as I told. Since we consider missing of a page as an interrupt, there exists a concept called service of the interrupt. What do you mean by interrupt service? So there is a standard procedure how to handle the interrupt occurred using interrupt service routine table. Interrupt service routine table. Okay, so we cannot do whatever the way we, I mean, process cannot behave according to his own way. It has to follow, it has to all the activities as per given in the interrupt service routine table. Okay, read the page as because you have got a page recently, read that page and then restart the process. Very simple way. Okay, because you missed you to perform activity, some resources were not available. You have requested, wait till you get a request. Okay, once you get a resource, read it, then start your work. That's it. Okay, so like how we've defined a cache hit and cache miss in terms of percentage, same way page fault is also explained in terms of percentage. Always if it is a percentage, it is called as probability. If it is a probability, it will lies between 0 and 1. 0 means not at all available. 1 means 100% available. If your request is page number 80, probability is 0. Because the frames are 1 to 35, requested is 80, definitely not possible to fulfill. If the resource request is 10, 11, 12, all are already in the page table, so probability is 100. So process will execute at a time. If request is 17, 18, 20 and availability is 17, 18, 19, okay, or the reverse, then partially it is available and partially it is not available. So it is in the range of 0 to 1. How to calculate the effective access time is 1 P is, okay, P. So something like 20% possibility of page occurrence. That means what? 0.02. Okay, so that we have to substitute memory access. P, 80%. If 20% missing, what is the possibility of occurrence? See, it is always you think they will not give both. Either of the part will be given. Okay, see, if we say 20% occurrence of rain today, that means 80% not occurrence, right? So memory access means memory access, one side 1 minus p here, 100 minus 20 is a 80. In the same way, memory access success is 1 minus p, memory access failure is p. Okay, memory access failure is p. That means what happens if it is fail? we have to find the page, swap out, swap in the page, whatever we request. So that into failure percentage plus 1 minus P into successful percentage. I hope you know about the cache. With respect to cache, you have did 1 minus P into cache hit plus 1 P into cache miss. That's what a formula you learned. Same way substitution. Now you can see memory access time is 200 nanoseconds. So if it is the access time, definitely what? It's a occurrence. It is telling about occurrence. Page fault is 8 millisecond. Page fault service means if one page service one page fault occurs, to make service, it needs 8 milliseconds. Right. So now here, what is the p value? What will be the p value? Probability. Okay. 1 minus p into 200 because it's a memory access time. You can see in the formula memory access time. 1 minus p into 200. Correct. Next, P into 8 milliseconds. Okay, 8 milliseconds. Now the one context important thing is both are in a different units. Please convert into same unit. Either you make this in terms of nanosecond or you make this average page fault in terms of milliseconds. Okay, so means same measuring unit. 1 minus P into 200. That means I am keeping the content in nanosecond scale only. 80 milli, 8 milli will become this much nano, because milli means here, what is your reference? 10 to the power of minus 9. Nano means 200 into 10 to the power of minus 9. It is 8 into 10 to the power of minus 3. Okay, so this, if you want to make a minus 9, attach 6 zeros here. We can see here, these are the 6 zeros we have attached. So both become 10 to the power minus 9. That is nanosecond time. Now what happens? Effective access time 1 into 200. Okay, plus 1 into 200 plus minus 200 time P. I will show here. Okay, 200 minus 200 P plus this much P. 8 6 zeros P. So this is the highest number, this is the smallest in terms of P. So what happens? 200 minus, okay, out of this if I subtract 200, so I will get 7,999, 800. 7,999, 800 P times. Now for 1 out of 1000 page fault, for 1 out of 1000 page fault, that means what? P is 1 by 1000. That means what? 10 to the power minus 3. Correct? So here you in the P space substitute 1 divided by 1000. So 2 zeros will cancel here and this will give us P. Okay, this will give us P. So now if we convert 200 minus this in terms of compromising middle, neither a nanosecond nor a millisecond, microseconds, we will get a 8.2 times of 8.2 times of, okay, sorry, one more thing, it should be plus. Why? Because higher value minus smaller value give us positive magnitude here. Okay, so 200 plus this much. Okay, 79. Okay, so if you convert this into here, so you will get a 8.2 microseconds. That means 10 to the power of minus 6 unit. Okay, what you need to do is, once you calculate this 200 here, 1 minus P bracket of 200 plus this big number, that's 8 with the 6 0, sorry, P times 8 with the 6 zeros. Right. So next question is 1 out of 1000 pages will be 1 out of 1000 pages will be a fault. That means P is 1 by 1000. So this will become 200 minus 200 times P plus 8 6 zeros times P. So highest value is plus, minus value is small. So what we will get is 200 plus 7,999, 800 times P. So P I substitute by 1 by 1000. I will get this value and I will convert into microsecond scales, and I got the answer of 8.2 microseconds. I hope it is clear now how to calculate. Same formula like cache hit and cache miss, how you calculated in your previous CO. Okay. So less than a minute is remaining. Give your attendance. I will try to continue the session. And as I told, I will upload the discussion on YouTube also. And also, whenever I will get a free time, I will record a session and store in that YouTube channel. Okay, because it is little time consuming, right? Okay. So next one is copy on write. Copy on write. Let me explain this diagram. There are two processes sharing a physical memory, process 1 and process 2. Okay, so process 1 and process 2. A page, B page and C page. These are sharing. So process 1 is controlling a parent, process 2 is a child. Process 2 is a child. So what happens? The process 2 will update something, it will update on page. So now, should the copy of page, whatever is modified, should it be updated in a physical memory, or it should be updated only in the process 2, like a local variable or a global variable? If it's a local variable,